Welcome to an overview of Stooge Sort. Before we begin, just a heads up that I use the terms array and list interchangeably. Stooge Sort is a divide and conquer or recursive comparison sorting algorithm that utilizes exchanges to swap elements that is deterministic, unstable, and non-adaptive. Deterministic meaning that with a given input, it will always return the same output. Unstable meaning that if there are duplicated values in the initial array, it will not preserve the order of those values in the sorted array, and non-adaptive meaning that its behavior is not impacted by any information it is given at runtime. Stooge sort can be defined as follows. If the value at the start of the list is greater than the value at the end of the list, swap them. If there are three or more elements in the list, then Stooge sort the initial two-thirds of the list, Stooge sort the final two-thirds of the list, and then Stooge sort the initial two-thirds of the list again. Here's a pseudocode example implementation of Stooge sort. So we have our function Stooge sort, which has three parameters, our array L, our initial index position, which is I equals 0, and our final index position, which is the length of the array L minus 1. So our first if statement checks if the value in the initial index position is greater than the value in the final index position, and if it is, then swap the values in those two index positions. So our second if statement is going to check and see if there's three or more elements remaining in the list. If there is, we're going to need to calculate a value t so that when we call Stooge sort later, that it's sorting at least two-thirds of the list. So then we call Stooge sort to recursively sort the first two-thirds of the list. We call Stooge sort to recursively sort the last two-thirds of the list. And then we have to call Stooge sort to recursively sort the first two-thirds of the list again. And then when we're done, we return the sorted array L. Why do we need to call Stooge sort a third time to resort the first two-thirds of the array? Well, here's an example. Assume we have an array with an index and values from 1 to 100. 1 is in the last index and 2 is in the first index. So the first thing Stooge sort's going to do is compare the value in the first index with the value in the last index. And if the value in the first index is greater than the value in the second index, it's going to swap those values. Since we have a value 2 in our first index and a value 1 in our last index, 100, we're going to move the value 2 to the 100th index, or the last index, and we're going to move the value 1 to the first index. Let's abstract every layer of recursion beyond the first. The first call of Stooge sort will sort the first two-thirds of the array. 1 will not change position because it's already been sorted into its correct index position. 2 will not change positions because it's not being sorted in the first two-thirds of the array. It's at the end of the array. Two-thirds of the total array is 67 indexes. Our second call of Stooge sort will be sorting the last two-thirds of the array. As a result, 2 moves from index position 100 to index position 33. As you can see, 2 is not in its desired index position of 2, meaning that if we were to stop here, we would not be returning a sorted array. Thus, the initial two-thirds must be resorted so that the index 2 can contain the value 2. And once that is done, we will be able to return our sorted array. That example is meant to highlight why Stooge sort needs to be called for a third time to resort the first two-thirds of the array. At this point, you might be wondering why this algorithm is named after the Three Stooges, mostly because I just mentioned it. After all, in the same time period there were three Marx brothers, but nobody has gone out of their way to label Stooge sort as Marxist. Stooge sort is aptly named because, while it has a linear space complexity, it has a computational complexity of n to the log of 3 divided by the log of 1.5, or approximately n to the 2.71. And that runtime is the same for the best, average, and worst cases. With such a terrible runtime, what's the point? Stooge sort is best used for educational purposes, as an act of protest, or algorithmic sabotage, as it will complete despite its terrible runtime. For ordinary people, Stooge sort is an example of what not to do.
We're not ordinary people. We're morons.
Yeah, but we're organized. Amalgamated Association of Morons. Local 6 and 7/8.
We are morons, tried and true, and we'll do our yell for you.
So with that example of Stooge sort users, some final notes. It can be reduced to a in-place base complexity with an XOR swap. You can also make it stable by tweaking the swap so that it searches for the desired element. This changes the inner loop to O of n instead of O of 1, but the computational complexity is unchanged because O of n to the 2.71 is still the dominating term. In either case, these are modifications away from the base definition of Stooge sort. They're just something to keep in mind. Also, Stooge sort, when run through a musical instrument digital interface, vaguely resembles classical music's sonata form. There's a example in the description of this video if you're interested. And finally, maybe the name comes from 70s proto-punk band The Stooges moonlighting as computer scientists, and I was the real Stooge all along.